So what is my theme? The session theme I'm talking about is insert, update, delete. And before I talk to you, I would like to talk a little bit over me. Because I'm brand new for the internal session. My name is Ricken. I'm from Germany. I'm a Microsoft SQL Server Master since May this year, but only until end of year. That was a great time to be a master. Yeah. Furthermore, what enjoyed me really was I became an MVP this year. In July, I have been awarded as an MVP. That makes me really proud. Okay, this is a little bit of stuff what you can read after the session. Insert, update, delete. What I'm doing with you is a deep dive into it. As you have seen maybe, as for my background, I'm a diver. Diving means you start on the surface and then you go deeper and deeper and deeper. Exactly, that's what I want to do with you. What I want to do with you when we talk about insert, update, delete, about the DMLs, is not to talk about you say, insert into, select, and so on. That's stupid. I think everybody of you know this. I want to look behind the scene. What I want to demonstrate to you is, for example, what transaction log does it generate if you run an insert? What if side effects have an insert if you have multiple indexes? And I want to show you the measures and what is inside, what is in the transaction log, what you can see when an insert, an update, or delete will happen. Okay, this is my agenda. Before we go to the DML, you need to be familiar with the internals. That means I talk with you about the internal structures, which means heap, clustered index. Just a second, I will remove these lines. So, looks better. Okay, I want to talk to you, first of all, of the SQL Server internals. That means we go, like a diver do, from the surface, step by step, down to the ground, to the rows. This is the final what we are talking about. And after this, or while I'm doing the demonstrations to you, I will show you several functions I'm working for investigation the transaction log. These are, for example, FN, first log formatter, and so on and so on. I will not explain it now, but I will explain it when I show you the demo. And I have lots of it. Okay, after we have our open water certificate, we can go diving on 80 meters and look around, look the corals, look the fishes, and so on. That's what we're doing with insert, update, and delete. What I'm doing is I show you the differences between a heap, a clustered index, and a non-clustered index. What happens when you insert, update, or delete anything? If the time is okay, then I will show you some bulk load scenarios. It's not always DML, but few things of this is DML. I want to show you the effects, the differences, for example, if you run a normal delete, or if you run a truncate and an insert into, for example. Cool. Okay. One topic before, if you have any questions, if there's anything, what are you saying, that's strange for me, raise your hand and I will answer it directly if it belongs to this slide. If it's something what I will explain later on, then I tell it to you and say, okay, a little bit later on. Okay, we start at the survey. That means that we start with indexes. Unfortunately, I promise I not want to tell you anything about index optimization. It's only that you need when you store data. You have three different kinds of storage elements where you can store the data. First is a heap. A heap is a very, very simple structure. A heap is only a table without order. That means you have a main node, this is the root, the IAM, and then you have directly under the leaf levels. The leaf levels contain the data. And what is important is each of these leaf objects doesn't have anything to do with the other one. So they are independent from each other. Yeah? So this means if you work with a heap, the data can be pushed very fast into it because there are no order means get into the data, get into the pages. It's completely different if you have a clustered index. But before I go to the clustered index, I want to show the first demo for the heaps. So I have to do it this way, unfortunately. Otherwise I can't see it. Okay, and here it is. Insert, update, delete. Okay, these are my demos. So enjoy. We have enough time, I hope. Okay, we start with a heap. And what I'm doing first of all is I create a simple table. It's a heap. You see there is no index on it. Simple table. And what you see is this table has only fixed size columns, int, char, varchar, datetime. Okay, what I'm doing now is I insert 1,000 rows into it. And now let's see, first of all, what is the fragmentation, or what is the structure of this index, of this object. You see only one line. This means you don't have a complex structure. You only have this one line, which means it's at the leaf level. The physical data structure looks a little bit different. Well, stop. Is it heap? Oh yeah, just a second. That's come when we play with it. Have I insert the datas? Cool. Okay. So, what you see here is the internal structure of this table. You have first of all the IAM page, index allocation map, and directly there you have the data pages. The data pages contain the data itself. And what you can see is, and this is really important to know, is if you see to the allocated page ID, there is no previous page, which means it refers to the previous page, and there isn't either a next page. So this means the page is completely independent. It's standing in the vacuum, let's say. Yeah. So what happens inside? What you can see, and this is the first function, fnfs log formatter. Who doesn't know what it is? Okay, every record will be stored on a page. And a page is the physical location. That means you have a file number, you have the page number, and what you have is a slot number. And this fnfs physical log formatter gives you the information about where this record, what you're looking for, is actually stored, and it depends on the index you have selected. So in this case, this means that my first record is stored on the page, on this file number 1, on the page 156 in the slot 0. Yeah? I will talk about it, what a slot is. So what I will do now is I will take a look into the page. This means I take the first one, this 156, and what I'm using then is dbcc trace on and dbcc page. dbcc trace on with the flag 36.4 means that the information will not go into the error log, but it will go directly to the client. And this is my SSMS. And what I'm doing now is I look into the page. What was it? 156. So, stop, this was the wrong one. I want to first look into the IAM, because this is the more important thing currently. It is the 163. Okay. So, what you can see here is on the page, the information, what object has allocated this page, and for me the most important thing first of all before we go deeper is you don't have a referrer to the next page and you don't have one to the previous page. And what is important too is that you have amount of approximately 8K free on this page. What you then have here is the single page allocation. That means the first 8 pages, if you insert into an empty table, will be single allocated pages. The reason is quite simple. Microsoft SQL Server does not know how much data you will get into the data, so into the table, and so the first 8 pages will be allocated. And what you can see is these are the first. Let's say the first is the 156. As you remember, when I made the select, this was the first page where data has been inserted into, and that's what I'm taking a look into. And what I'm looking into is what is the page header. This is the information about, again, what is the object which owns this page. And what you can see, very cool, is we have 16 records in this page. And again, next and previous page is empty. We have approximately 1,360 bytes free on the page, and it starts at position at offset 6,800. Furthermore, here are my data. I think it's not possible to read it currently, but you will see how you can do this. And if you see the transaction log, it's important to know how a record is structured. Cool. Any questions to this part of the scenario? Cool. Then we go to the next one. This is a little bit more complex. This is the clustered index. A clustered index instead of a heap is an ordered structure. Simple say, let's say you have a parking garage and you can enter the park garage. In a heap, you can stand wherever you want. If you have a clustered index, that does mean there is an operator standing in front of it, and when you come with your car, it gives you direct the information where you have to put your car to. This is the difference between, and what you see is we have a hierarchy. The hierarchy does mean if you're looking for a record, it can completely come from the root to the so-called intermediate level to the leaf page where the data resides. A heap or a clustered index is the table. This is something, well, sometimes I'm often hear that the clustered index is the copy of a table. This is nonsense. The clustered index is the table itself. So on the leaf level, there are the data. And that's what I want to demonstrate to you too. I take this one. Okay. Exactly the same what I'm doing. I create now an object, same structure, called TBL cluster, and stop, there was an arrow. Okay. Cool. And what I'm now doing is I'm creating only a unique clustered index. Unique means, okay, the cluster key values are unique to the keys are unique in the table. And now I insert 1,000 records. I put in the default values, it's only for demonstration, and now I look to the fragmentation of this object or to the object structure. These DB physical stats give you more information, not only the fragmentation, it gives the information about the levels you have on your index. And what you can see here is that we now have a structure. The heap had only one row, as you remember. Now we have two. This is my root level, and now here's my leaf level. And what you can see is the dependency between the page count and the record count. That means on the root, we have the administration. The operator has a list, and it says, hey, I have 53 pages where my data reside on. And these 53 pages take 1,000 records. One word concerning the fragment count. You're wondering why you have a fragmentation count, or you have fragmentation in your index. You haven't. This fragmentation count does only mean that the pages will not be each to the next. That means you have page 1, 2, 3, 4, 5, but that the data have been on the page 1, 2, 4, 5, 7, and so on. If you have a gap between, this will be counted as a fragment. But you don't have to worry about it. If you fill the first time your table and you have a fragmentation count, don't worry about it. It's only that you have a gap between two of the pages. And you can see it here. Just a second. First of all, I show the structure. This is the structure. I use the DMDB database page allocations. It's only in SQL Server 2012. Otherwise, you have to use dbcc int. Okay. So what I see here, it's completely different as we have in the heap. We have our we have our starting point, and what we have here, the IAM page with the administration for the whole object. And now we start in the root with this, which is an index page. The index page is concerning the structure of my table, the top level. I start from it, and what it says is, here we administer all our parking areas, if you think in the parking garage. Here, my operator is sitting here, and he administers every of my parking decks. So, and what you see here is that this index page, the first one, is the 171, and let's have a look to it. Let's see how it looks internally. Here, stop. Stop, here it is, 100 and, what was it? 171. Okay. So what you can see here is you don't see the real data. Why? It's not usable, because the only thing what I need to know is, hey, the operator need to know what parking decks do I have. These are the child page IDs, which mean whether it's under this B tree. And then what you see is the key range, the slot or the keys where the objects are reside. That means on the page 168, we have from key nothing to key 19. That means every car, when numbered from 0 to 19, is located on this page 168. Yeah? And that can be seen. Let's make it visible. 168. Okay. So, okay. First of all, I look only to the page. Oh yeah, cool. You see what I've forgotten? The trace flag, yes. It's, in my case, it's only for the session. Cool. Oh, there is a typo. Don't type in the... Okay, here's my page. The only thing I want to show you currently is look to the previous page and look to the next page. These are the referrals I talked about. That means that now in this situation you have the pages which have suddenly a relation to each other. And due to the fact that I've started with the first page where my first data are in, I only see the next page. And this is important because if you make a table, if you make a scan through the data, what does the SQL Server Engine need to know? It needs to know, hey, I'm on the end of my page, where is the next one? And the overnext, and the overnext, and the overnext. So therefore, it's important to have a next and the previous page. I have 19 records in my page located, and I have only 97 bytes free, which is on the offset 8057. I hope it's until yet very simple. Let's see inside the page. And what I will do here, first of all, I show it in a normal text way. And what you can see here, and this is one thing what you should consider for the next thing when you go deeper to the rows. What you see here, here's my rows. Yeah, you see it here, and you see the data here. And what you can see here, here it is completely recalculated. You see the real data. You see the slots, and you see what value is in. This you can get with the option 3, but it's in my demo. Okay, but what will happen if you have a non-unique clustered index? It's important for you to know if you don't have it, you will have a much more overhead for administration. I will drop my table and recreate it, but now the only thing what I'm doing is I create a clustered index. That means it's not unique. And what will happen now is I insert once again a few records, and what I'm doing now is what you see here, just a second, I have to run zoom it. Cool, okay. Here it is. What I'm doing is here, I'm producing 1,000 records, but the ID value or the keys are redundant. Yeah, that means that we get redundant data. Okay. I insert 1,000 records, and now have again a look to the structure, but you see the structure. Okay, what you will see here is that the structure is always the same. Yeah, but it's not the difference what you see obviously, but the difference is in behind. Here you see where the data are located. You see the records are on the, it started on the page 177, and we have beginning slot 0 and contiguous. Cool. Now what I will do, I will have a look into the B tree first of all. Therefore I have to redo it. The B tree starts at page 179, And let's see how it looks inside. Here it is. Suddenly you see not only the cluster key is part of a B tree, but now we have a unifier. So one important thing concerning the unifier will be shown when you look into the page. And this is, one moment, let's look, it was 177, yes. This is one thing which is important for the next thing. Okay, what I'm doing now, I exactly run the same DBCC page, but now I give it a better output when I use it with table results. This is only that you get it in a grid, yeah, instead of plain text. And what I want to show you here is unifier. You see it starts with 0. This is my ID's -1. This was the first value I've inserted. But now I come to the next one. Here it is. The ID 0, ID 0, and here I have a unifier. Do you see it? Here it starts with 1. That means that the key value 0, this is the second time it has occurred in my cluster table, clustered index. One question to you is, or to everybody is, how large is it? How much bytes does a unifier consume? It consumes 4 bytes. That means if you have a cluster key is 4 bytes and you have it not unique, then you transport 4 additional bytes with your clustered index in the cluster keys. But one question is, what happens, and this is one thing you should keep in mind, if the unifier is 0, that means that the very first value you have, and let's say you have 1,000,000 rows and you have, let's say, approximately 10 to 20 or 20,000 records which you may have duplicates, not so problematic, because if you have the unifier 0, the physical length is 0. It doesn't contain this as the physical value on the page. It's only an information. In the moment it starts with the next one, it counts up. Then it will be filled, and then it becomes physical. And you can see it with the next one, where at the 1. Here you see that it's a physical 4 bytes, what you store on the page. And this is storage which get lost from you for the page for other information. Okay, clean the kitchen. Any questions? Oh, where stopped? Here it is. Any questions, someone? Cool. Next one. Anatomy of a non-clustered. It's a very complex thing. So this is the reason why I have used the picture from Microsoft. Otherwise, the slide would fit the information. Here, the non-clustered index is quite simple. A non-clustered index does only contain key values, not the data itself. And the non-clustered index will contain on the leave node, on the last level, the keys and possible included values, if you run an index with an include option. If you have to have a lookup to other data which are not part of the index, you produce key lookups. And I think it's a thing, if you were in the track with Kale and Delaney or any other, you have heard about it. So that's what I want to talk about, clustered index, non-clustered indexes. Why is it important? It has to be maintained. So that means if you have a table with a clustered index and with 10, for example, 10 non-clustered indexes, that means if you run update with only 1 row, you will produce 11 entries in your transaction log. 1 for the table itself, for the clustered index, and 10 for your non-clustered indexes. So you have to think about the complexity. And this is what I want to demonstrate to you. Cool. This is important. Sorry, I forgot it. One more demo. I have too much of them. So, but I think this is non-clustered. Yes, cool. Okay. I hope that all the scripts with the presentation will be shipped. I think that we can download it then from the SQL website. I create a table, exactly the same. What I'm doing now is I only create an index, but not a non-clustered index. That means I have a heap and a non-clustered index to it. So no order on the table. What I'm doing then is I insert again a few records, 1,000 of it. That's the maximum my computer can do in the meaning time. So we are short in time. I wanted to reduce it to 100, but then my demo will not work. So what we now have here, remember that we have one index, but we see 3 lines in the result. The result set means that you have one of the heap, that is the index ID 0, and you have this ID 2, which is your index or the index I've created. Keep in mind the index ID numbers, because when I now want to see the data in its physical location, I can do it. Come on. I give the index ID or the index name to it. If the index hasn't a name, for example, the heap, then you give it with the ID. And the ID is 0. That means I want to see where are my physical data located on the pages. So 163, there it starts. And what you can see is if you do it for a non-clustered, this is when I do the ID 2, then I get completely different pages. This is exactly what I said when I say maintain indexes. If you insert records, it has to be inserted on the table pages and on the additional index pages. And you will see that in the transaction log. Cool. Okay, now what I want to do is I select the location for only one record. What I have done here with my query is I select only the ID, which is 99, and I do a select with the union all from the physical location on the heap, and the same with the physical location when I use the index. And what I get is these two pages, 175 for the heap, excuse me, and 165 for my index. What I want to do now is I want to look into it. Stop here, yeah, this is my non-cluster, it's 165. I want to look into the page, and what I get there is a very interesting thing. First of all, I see my key. This is what I said to you, that the non-clustered index only contains keys, not the data itself, otherwise, if you have, for example, include inside. But what I have here, I have the row locator ID. The row locator ID is a hex value. It's only available if you have a heap instead of a clustered index. And you can read this RID. The RID defines the physical location, physical, not really physical and logical, because slots does not have to do with the physical location, but this RID determine where you find the data in the heap itself. And it can be decrypted. It looks very horrible, but it's quite simple. And what it do is it only gives you information. I copy it to this here. So 1 second, go. So 1, 2, 3, 4. 1, 2, 1, 2. Oh yeah, I have to count. Okay. So what I'm doing now is I take these values and put it. These are hex values. I put it into a decimal value. And what you can see there, oh, come on, so press the wrong button. F, 01, okay. This is information where my physical data are. So the RID is always, don't let you tell anything others, the RID is the location on the heap. But it's a unique it's in hex code. It's we have count. It's 1, 4, 8. It's 10 bytes. Horrible. It contains it consumes data. And what I'm doing now is I create a unique clustered index on it. And what is now the complete table and the index has been rebuilt. Very simple because it is. The reason is quite simple. Due to the fact that I don't have a heap, the table the table has to be reorganized concerning the sort order, and this means that the location of the record changes, and this has to be mirrored to the indexes too. So I want to see this. This is my index 2, and I want to see now on this page how it is. How does it look like? Instead of a RID, what do we have here? It's 294. 294, and what you see now is I have the key. It's only 4 bytes. It's less of data. And every time when I'm thinking about DML, I think about the data of the transaction log, for example, what I produce every time when I run any DML. And this is something I would take into consideration. Okay, clean the table, clean the kitchen. Any questions? Cool. So, just a short summary. If you have a non-clustered index on a heap, you will store the RID. If you have it on a clustered key, you will store the clustered key. Cool, I think that's a thing everybody knows. What we are doing now, we're on the surface. That means we go now deeper. What you have seen currently, and this is important for the analysis of the transaction log, is to understand how Microsoft SQL Server stores this data. We have three different kinds of data. We have in-row data, we have blob data, and we have row overflow data. And every data part has to be stored in a different way. So, and the hierarchy is very simple. What you see on the surface is only this object itself. So that means, look down, index, that's what we have done. But there is not much more about it. What we have is an index can be, or an object can be partitioned. So that means that you can separate your data into different partitions. Cool. And every partition has different type, or can have different type of data it can store. It's not separated by, okay, let's say partition 1 is only allowed to store in-row data. No, it can have all three. No problem. It depends on the architecture of your table. And that's what I want to demonstrate to you. You can query these objects. You start at the top with these indexes. From these indexes, because it could be partitioned, you go to this partitions view. And under it, then you see the allocation units. So that means every partition can have different allocation units, types of allocations. Let's see how it is in real life. So here it is, yes. This is so. Data storage internals. Cool. So every time again, again, my table, I have just a heap. There is no inside. Okay. So you see, it's a heap. Okay. But now I want to look how this data is partitioned. You know it. I've seen it. I have only one partition, but that's what the system will show me. If I query this indexes joining with the partition, then what you can see is you have to join it over the index ID and the object ID, and additional to the data space ID. And what I see here, surprise, surprise, just only one partition. And the moment you create a table, you only have one partition, unless you're doing it in a different way. What is important here, you see currently what is my partition ID. Take care of the HOBT ID. Hobbit, some people call it Hobbit. It stands for heap or B tree. What is a synonym for it could be a heap, or it could be an index structure, clustered index. Yeah. And what is important too, you can query how many rows are currently stored in this allocation, in this partition, and are the data compressed. Very, very simple. Okay, and now we look to the allocation units. What do you think? Think about the structure of my table. I had an ID, 2 character fields, a date time. How many allocation units do we have? It's just one, because every data type is an in-row data type. And our table has not reached the max of 8,060 bytes. Yeah. So we see we have now the in-row data. We have non-pages in it, and that is really, really important. When I start my inserts, my insert demo, think about it that in the moment you create the table, you don't have pages in it. Okay? Good. What will I do now? Now I change my table. And what I'm doing is I add an image, a variable max, a text, and 2 additional. No, this is not. No, this one, this is a test from me. Okay, I add two additional columns, an image, and a varchar marks. And what I now have, when I go and look to the allocation units, I have 3 of them. That's cool. That means that Microsoft SQL Server separates each data type into different allocation units, if required. Yeah. So the log data is from the image, and the row overflow data is from the varchar max. And that means for the transaction log, every allocation unit, if you insert a record, has to be treated separately. Yeah. Okay. And clean again the kitchen. Any questions? Yes, there's a question.
Is there a way to find out which logic of file name an object belongs to?
The question is there a possibility to see the logical file name, no, the physical file name?
The logical file name that an object belongs to, not the file group, but logical file name.
You
understand the question?
Yes, I understand. Yeah, if you have multiple files and you want to know where the data is on.
For some users design a database, they add multiple logical file names to the same file group as
Yeah.
the primary file group, for example.
Give me a chance for tonight. I will check it tonight. I currently do not know.
I think that will be the page, the file ID.
The file ID, yeah, but it's only the physical file. So I will take care of it after the session. Okay, I do not know currently.
Not the physical.
You want to have the logical one? Yeah. Give me a chance for after the session. Okay.
Yeah.
Another question?
Oh, well, that was just the answer. It's in all of them.
Pardon?
The table is in all of the files.
The table is in all in the. Let me check it after the session. Yeah. So I'm currently a little bit. I will see it. We can do it after the session. Okay? Good. Okay, the next one, we'll go deeper. We're now allowed to dive 8 to 9 meters. That means they can see a little bit of fishes and a little bit of the corals, but we go deeper. We go now to the next part where in the hierarchy of storage. We now knew the allocation units, and what we need to know is where will data be stored? It will be stored on pages. Every page has exactly the same structure. It means we have a page header, and then we have the data itself. And this is a very interesting thing. I will demonstrate it too. Let's see what's the time. Is it really? Oh, cool. I think that I will. Oh, this is amazing. Give me 120 minutes more. Okay. Okay. I think that one thing I need to know. Let's skip it, the data page. I will go directly to the anatomy of a record. It's more important to understand when you read the logs. Okay, otherwise, if you're interested in, then we will do it afterwards. Anatomy of a record. That means now we are on 80 meters. We are near the open water dive certificate. The record is the last level of information you store, and the record has always the same structure, and this is important to know how it's working. And what you see is, and this is from Ken Delaney, every record is defined into several parts. The first 2 bytes are exactly for the status byte, for example, fixed length, and so on. And what I do is I will demonstrate it to you in a short demo. What I do is, come on. Once again, my table, checkpoint, select, blah, 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 and I insert into. The only thing what I want to make sure is that now I don't have any records in my transaction log. I have running in the simple mode. Okay, nothing in. I insert the value, a record into my table, and what I see is, let's see where it is. It's located in page 156. Great, cool, okay. But now what I want to know is what happens in the transaction log in that moment. And this is a very important thing and a very amazing thing if you don't know what happens really. I look into it and see, oh, 1 record inserted. Wow, good stuff. No, it's much more behind the scene. This is only the thing what you see from your insert statement. But what is important now? First of all, you see the allocation unit. The type of data which has been stored. The next one, what is important, this is your allocation unit name. You see that it's imported or inserted in my table at page 100. This is a hex value, slot ID 0. Imagine your car garage, you have many slots, and this is the first slot, and in this slot there is my car currently standing. And what I have now is here my record. Excuse me. The roll content 0, if you run an insert, will give you the information about this is the record you have stored, and this is an hex value. And when you see this value, and I drop it down, this is my value. This is the record in the binary mode. And this is everything what you see in the transaction log. And what we need to know now is how can we decrypt this information? Yeah. And what we will do is we have to separate these information into different portions. First of all, I take care of the first 2 bytes. The first 2 bytes give you information about the kind of row and if the record is a ghosted forwarded record. The definition is as follows. We start with the first byte in the bit 0. This is for versioning. Forget it, it's since SQL 2008 always 0. The next 3 bits, these are very important. They define the character of your record. What kind of record do you have? So in most cases, if you look into the data pages, you will have primary record, that mean normal data records. But what will happen, for example, if you have a forwarded record, I will demonstrate what it is, or if you have a forwarding stub and so on. These are all types of records which will be stored on your data page. And this is what you think about is, everything what you store is a record. Whatever you do, it's always a type of record. The 4th bit, or in this case, the bit 4 is the null bitmap. I will explain it later on, and the columns and so on. Let's start with it. Unfortunately, I give the surprising result in this case, but okay. See our insert statement. It's inserted into blah blah blah, and what we see if you open the page, you see that my record type is a primary record. We have null bitmap, okay, and my record size is 70 bytes. So, and now what I do is I take this record and now I analyze it byte for byte. You see the 30. 30 is the hex value, is 48 in a decimal, and this means in a binary value that the offset 5 and 4 is on. As you have seen in the slide before, we only have the bit 1, 2, 3, which defines the type of record. And if you look to it, concerning to our example, you see it's a primary record because the offset 1, 2, 3 is 0. Yeah? Cool. And 0 means primary record. So that's a calculation. The next thing is the fixed length size. And this is a very efficient way from Microsoft SQL Server storing data. The hierarchy is quite clear. Header, then comes the fixed data. Nevertheless, where the position is in the table, the fixed data will be the very first which will be stored in the record. And this means, in our example, we see the 38, which gives you the offset, where the fixed data ends. So 38, I have a math program here, you see. It's 38 plus 0, 0 is 56. 56 bytes, that means the offset is nearby here. But 56 bytes is always, and everything what you read here is from the very beginning. So that means I have to reduce it by 4 bytes, 1, 2, 3, 4. And that means that the next 52 bytes containing data of your fixed data portion of the table. That's cool, and this is my value here. And here, see, it looks horrible, but it's very simple. If you take a look, if we take this data and compare it now to our data structure, we have an int value. This is my first attribute, 4 bytes, 20 bytes, 20 bytes, and so on. You see that the first 4 columns are only fixed length columns. So, and what I'm doing now is I decrypt it. This is the value 1. And this here, please take in consideration, this is always 1 byte, 44, it's a D, and so on. And this is Donald, Daisy, they have married at the 21st of March. Congratulations. No, this is my marriage date. Okay. To demonstrate it that it's true what I'm saying, I give you a very, very simple part. What I'm doing is, there is something I prepared for you. It's exactly the values you have seen here. And when I do a select from my table ID with a union with my converted binary values, what would you expect? What it is exactly the same. So that's the way how you can decrypt the information which was stored in your transaction log.
Question?
Yes.
Why would I want to do that?
Yeah, to understand what happens in your transaction log. That's the reason why you're sitting here.
Why would I want to do that?
Why you're interested in. So I'm interested in when I'm talking about workloads.
Value to it, it's just like for fun.
Pardon?
So there is no real value to it, just for
For me is, if you understand, yeah, it's important to see when you run an update, for example, what happens if you only update one character.
Yeah, what can I do about it?
It's an information, it's learning, it's knowledge transfer. And so if you're not interested in, then it's,
I'm not trying to figure out where
yeah. So what I want to explain how a record is structured. So if you're not interested in, then sorry, and it's, if you're not interested, you can go. Excuse me, I want to explain how it is. So we can debate it after this session, okay? Okay, so the next one is in the anatomy that you can see the number of columns, which mean that it's the seven columns, and so on. I will skip over and go to the next one. It is the variable character, a variable length part of it. And this is the most expensive part, because every time you have a variable length, the Microsoft SQL Server has to calculate where is the offset. Yeah. So, okay. Then I will skip it and go to the demo, merit, and so on. Okay. Good. Insert data in a heap. We go with the heap. And what I'm doing is I'm clearing the log and check whether it's clear. Okay, and then we start. What I will do is I start it in a separate transaction. That is the only possible thing to measure how much bytes your transaction consumes and what logs do you have. So, and what you have, I start it, what I'm doing is I give it a name. If you give it a name to a transaction, that's possible for you to select to filter for it in the transaction log. It's the easier way. Good. This is my name. And now what I'm looking first of all is I'm looking into the locked objects. And there is something special doing what is not really obviously visible. You see that I have a locked lock of my key. This is okay. This is an intended lock on my page. And what I have is an additional object lock, intended exclusive lock. This is because you have an identity value in your columns. If you have an identity column, it has to be managed outside of your transaction. It's a separate transaction, but it consumes space, and it has to transfer it to mirrors and always-on groups. Okay, and the other part is to see the amount of data. You have 464 bytes, which consumes your transaction. Okay, so what you see is here, what happens internally, this is only this one row which has been inserted. This is obviously what you see. But now, remember that the table was empty and see what happens in detail. And this is here. Now I see everything what happens. And this is a more interesting thing. And think about SQL Server as a lazy operator. A lazy operator who has kids. I think most of you. Do you know the situation when you say, "Hey dear, can you please bring me a beer?" What did she say? Or in my case, yes, she say, "Yeah, Daddy, when I am in time, when I go wherever then I do it." And that's exactly how Microsoft SQL Server is working if you run such an DML. If you have a plain table, a new table, the table is physically not there. This means when you build a house, for example, what will you do? The first step is you hire an architect. And what is he doing? You're doing a plan. And that's exactly what you do if you run the create table statement. And that's what you can see here. The system is creating the table in that moment when you insert the first record. In that moment, the data or the table will be physical. And this is the amount of data what happens internally when you create an object. Yeah? So you see only the 460 bytes, but internally there's much more. Okay, free the lock again. And now I insert a next row. By the way, this is my daughter. Okay, see the transaction log again, and you see again this page, this object has been locked. This is the identity column, which has increased to 2. And again, the amount of data, you see it's exactly the same because it's only this amount of data which is in your transaction. Okay, inside you see that we have much less. This is the only thing what happens. Yeah, we have only this insert. So the complete rest of it, the build up of this house is not part of this transaction. This is only the first time when you insert a brand new record. Okay, now what I'm doing is I'm insert 100 records in my database, in my table. This is 35K, which consumes, and now I want to. Okay, see. First of all, I want to see the data where it is. You see, it is on its page 164. Keep it in mind that is the first page where data are. And what I'm doing now is we have 32 records which are located on this page, and the next one starts at the 166. Okay, so what I will do, I will delete 2 of them, the 32 and the 16. And here, okay, they're not in my table. And you see that the slot is free. It's like a park garage. And the moment someone is leaving a slot, it's free. Yeah? Okay. 164. And the record 16 again. What do you think what happens? What has happened if I inserted the number record? Keep in mind that it's a heap.
It's just added to the end.
It's added to the end. Yeah. It's added to the end. And the reason is quite simple. It's because Microsoft SQL Server is a lazy operator. I want to show it to you. The 16, here it is, at the end, slot 4. And this is, think about the operator in a car garage. You're coming in, no rules, everybody can do what you do. So now what you have as an operator is only a list for every park deck, what slots you have available. And now think by yourself, what would you do if you're an operator and you're a lazy one? The first look, what you will do is on the very last page. And if you see there is enough storage, there's enough slots free, then you lead him to the last page. Yeah, the system is scanning in this way the information from this slot array, and if it see, hey, I have to recreate a new deck, for example, for a new one, then it say, okay, give it a place wherever it is free. This is what I want to demonstrate to you. So that the 32 is the same, and it is at the very, very end, the same way as it was with the number 16. Here, the next slot. Okay, now I clear the table again, and now I put in 96 records. And this 96 records mean that I now have a table the last page completely full. This is the very last record which is on this page. I've calculated. So, and now I delete again these both records. The same situation, and now you see they are empty. We have the 16 away, and we have the 32 away. Cool. So what I'm doing now is I insert this record 16 again. And what will happen now is that in that moment, the 16 is in the slot 15. And this is because it's a lazy operator. You're sitting there. He's too lazy to say, this is too expensive to build a new page. And that's the reason why I put it on the same page again. Yeah? And that will be exactly the same with the 32. Okay. Any questions to this?
Could it be the other way around with 16 in 32?
Excuse me?
16 in 32, if you did it the other way, right?
When I put in the 32, you mean? This one?
Yeah, was it because you did it in this order?
No, the 32, there is no order in it.
Yeah, exactly.
Yeah.
So you could put 16 in 32.
It could be, yeah, it could be. I do not know whether SQL Server is doing it. That's a magic logic behind. Yeah. So the question was, if I put the 32 in the first insert after I've deleted it, will it be in the slot 15 or in the slot 31? Don't know. It could be, but must not. It's depending on the logic of Microsoft SQL Server. One thing is very important. Think about a forwarded record. I have to shorten it, unfortunately. Think about a forwarded record. A forwarded record is nothing else if you move to a new location and then you go to the post office and say, hi, there are some letters for me, please send them to my new location. And this is the same with a forwarded record in a heap. And if you have variable length columns, it's predicted for having forwarded records. Why? If you get new long entries, then it doesn't fit to the page and will be forwarded to another page. So that's one reason why it could be a good practice to have fixed character lengths. Yeah? So, any questions to this? I will move on, I will give it everything. Same with the clustered index. Now it's a completely different scenario. Think about, while I'm doing this inserts, think about a clustered index like a park garage where you have rules. And the rules is that if a car is coming in with a number on the plate, you have to take care that it's always at the correct position. That means at the correct parking deck. Okay? So this we have seen, okay. I free it and I go to the next one. So now I insert one row again and see what happened. I insert into a value 5, this is a new one, and one row exact, but see the transaction logs. Okay, this is nothing special, but now I see the transaction log, the amount of operations, 470 bytes that consumed. Okay, this means that the data has been inserted very well. Okay, now I want to do a page split. Page split is very, very expensive, and I want to demonstrate how expensive it is. I truncate the table, empty the log, and now I insert 100 records. I didn't. Oh, sorry. Just a second. Thank you. Okay, yes. Cool. Thank you. Okay, I truncate it, run a checkpoint, and now I insert a few records. So 11 kilobytes of data. See the location of the data. And what I see here is I have only 1, 3, I have a gap in between. And what I will do, I insert one new record. Please keep in mind that now the pages are completely full. And so what I will do now, I insert one more record. You have seen 472 bytes for a record. And now I insert one new record completely. So begin the transaction, see the, insert the record, and now see what, come on, wrong. Okay, what page, what objects are locked. And now I see the huge amount of, correct, yeah. This one has fit to the page. You see it has 488 bytes. That consumes 488 bytes, this transaction. And now I get another one. Begin the transaction. I do exactly the same now. Yeah? Insert one new record, but keep in mind, it has to be in the order because we have a clustered index. And now I see what the amount of transaction I have consumed, and oops, nearby 18 times more for only just one insert. And the secret is in the transactions, what happened here. What you can see here is when I look to the whatever, here's 70, here it is, we have a break here. One, where is it? 77, what value is it? 16. It has been here, yes, and 17, stop, up, here is the break. It has been splitted. And the split is a very time-consuming and a very, sorry, that was my door again, so here it is. It's very, very transactional consuming. This is all the transaction what has been done when a page split occurs. And the page split, put it in a way as you have a garage again. And what has to be done, first of all, what you can see is every object which are involved has to be part of an internal transaction, and then they start to do the page split. That means we have to free space in the PFS, we have to zero the new page, we have to mark the pages, we have to run modifications to the header, and so on and so on. That takes really, really much transaction log. And that's the thing what you have to consider when you're thinking about inserts of data into your table. So I see that I'm completely overdue. I'm really sorry about this, but first of all, the technical problems. What I would offer to you is everybody who is interested in, I would do the rest of it, but only the demos without any deeper explanation to it, so that we can think approximately finish in 10 to 15 minutes. I hope this is okay for you, if it's interesting enough for you. Yeah, thank you very much. Cool, okay. Yeah, okay. Have a good dinner.
The dinner starts within an hour.
Within an hour, yeah. So it's not really very much, but I will demonstrate the rest of it. Completely overscheduled. Sorry for this.
How much is SQL Server 2012?
Everything. Everything what I'm doing here is completely done in SQL 2012, but I've tested it in.
How much will be done in 2008?
Exactly the same.
Okay.
Definitely the same. Yeah. Tested in both. Yeah.
There were a few DMVs.
The last one DMV concerning the structure of the data pages. This is brand new, as I told you. In SQL 2008, you have to use dbcc int instead of this DB database physical pages over. Yeah. Okay. So thank you very much for being here. I think a lot of people are here interested in. Okay, then I will not try to stop it. The page splits. I told you that it is a very expensive thing. Let's go to the updates of a heap. Updates of a heap can have many, many side effects. And these side effects I want to demonstrate to you, this forwarded record. Simple insert of data is okay, we have done it, checkpoint, insert, and now I insert a few records, done. This is that every script I prepare the environment completely new. The checkpoint is only in a simple mode, interesting, that I free the transaction log. Now I update a column with a brand new value. That means I take one column and now I update the information and see what is the consumed transaction log. It's very less, 296 bytes. This is very simple in a mirroring or in a high availability system, very fast transferred to the value. But what you see is this is a brand new text for me. This is a brand new text for, just a second, this is, yeah, here. Just a typo, a Brent. Yeah? One character. What do you think? If I now run an update, what will be updated? I will show it to you. You will be, this is really, with respect, this is really, really amazing. So I run my transaction, update this ID, and what I now see is the amount of data, 240, fine, okay, but what happens? And this is a very interesting thing, just here, okay, this one has to be taken. Look to the offset in row. This is a really interesting. That's the reason why it's important to know the structure of a row. In the row, at the position, at the byte 22, there occurred an update for, one character. You see, this is the hex value 64 has been changed to the hex value 74. This means that the transaction log is Microsoft SQL Server is, as I told you before, a really lazy operator. It doesn't change the complete record, it only changes just one character. And this is a really amazing thing that Microsoft SQL Server recognizes, hey, only this one character has been changed. Why so much overhead? Change only the part what need to be changed. That's pretty cool. So this is the, check the amount. So once again, cool. I think so, yes. I no? Yeah, this is every time the same. Cool, okay. Okay, good. Okay, if you run an update in a, I have seen it in many developed things where updates occur, they put make an update, put the next text to it, put the next text to it, so they update frequently the same attribute. Don't do this, do it in one. I think it's clear what will happen if you do this. Didn't? Okay. Thank you. Okay, if I now run 3 different updates, always on the same column, it is not handled as one. If you think this is handled in 3 different ones. This is the amount of space you allocate in the transaction log. And this needs to be transferred to the mirrors or to the always on objects. So this thing is quite clear. It happens so that we now have 3 different updates, 3 different update commands, and this is time consuming. Okay, we talk about very huge and very fast RAM and speeded databases and so on, but it consumes amount of data, and every consummation of data means time. Yeah. Okay. No. So now I run an update on an variable column. So let's see where the location is. I run it here, just a second. Yeah. Update this is a replacement, so I run the transaction. I run an update, and I want to see how much. Pardon? Okay, sorry. Okay, now the next is check the difference, update. Check the difference of log amount. Just a second, measure to log bytes for each update. I will go very fast through it. Yeah. Amount of log byte each update. Come on. I will replicate 100 times the object A. I want to see the page split, the forwarded record. Just a second. Tick, 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 tick. Okay. Yeah. What I tried to. This is very interesting. Once again, I made an update on the table. I changed the value to A 100 times the A, and I did it again. But nothing happened. This is interesting too. I thought that every time you run an update, it will consume transaction log. No, it doesn't. If the system detects, hey, it's exactly the same value as you have, then it will consume any transaction log, and that means no transfer to any mirror, for example. So, forwarded records. Okay, this is the thing I want to show you for the heap, and then we go the farce to the clustered indexes. And then we are finished. So, what I will do now is, first of all, this is my pages, 290, I want to know it. And what I see, first of all, is the I/O I produce when I do a clustered index scan. So therefore, I started the statistics I/O on, and that means that I see the information. I have 1 page on it. Very, very simple and clear table. Excuse me. Okay, so my page is exactly, it has 32 records, meaning that fits perfectly on 1 page. And I don't want to see it, make a checkpoint. And now I run an update. I write 100 characters into the column 2, which is my variable length column. So I start my transaction and I run an update. So see what happens, the update, 464 bytes, perfect. Yeah? Okay, committed. Now I run it again. See, first of all, do I have more IOs? No. And now, come on. I expanded to it 200 records, 200 characters. Run the transaction again. replicate it 200 times, and now see what happens in my record, my transaction. 2,200 bytes now. And this is that means it's a very expansive operation inside. And this operation can be made visible. Hey, commit transaction, yeah, okay, yeah, now it's clear. First of all, the first thing what you see is when you run the statistics, you have one more I/O. 2 more I/Os. Cool. So what happens internally? And what has happened is very simple. One moment, here it is, 290. 290. I want to see the page. And there you can see I've updated the ID too, okay. Come on, primary record, the first one is a normal record, and the second one is a forwarding stub. So this means the same as when you move to another address, and you go to the post office and say, hey, if you get any excuse me, any letters from me, please ship it to my new address. But one thing is really crazy. I have only one new page, but you have seen I had 3 I/Os. Do you know why? Yeah, you do. Yeah, no, excuse me, I ask you. Do you know we have 2 pages, 2 leave pages, but I had 3 I/Os. Why? What do you think? Make it long story short. This is my updated column. You see it's in slot 1, but please consider now we have a forwarding stub. What means the engine now reads the first page, where is the first slot. Now it comes to the slot 2 where it says, hey, I'm not here, you have to go to this page. Now we have the next I/O to the second page. And then come back and read again. Cool, 3 I/Os. Yeah. So forwarding record is quite expensive, could be a quite expensive mechanism. And here you see it. We have 2 pages, which we read, but we had the I/O through because it was jumping. Okay. So this is the reset the length. Yeah, this is an important thing I want to show. I update it and see the amount of data. What? Did I do it? One moment. No? Okay, one again. So what I want to show is, in the moment the record will fit to the page again, the forwarding stub will change back to a normal primary record. Excuse me. Okay. Next one, and the really last one then after the update. So simple insert you have done. The clustered index is a completely different one. So the clustered index, instead of a heap, works in a completely different way if we run updates. You have seen it could occur that we have page splits. Page splits are expensive. Yeah? So insert few records, go and sometimes I have to run it twice. Okay, I update the record. It's always the same. There will be no difference. I start my transaction, made the update, and then I see what consumes, what transaction login it consumes. Oh, there was, you see the checkpoint didn't work. So one moment, and I update it. Cool. So this is okay, this is okay. I will skip this. Okay, good. So clustered index is exactly the same as it is in a heap. The operations are exactly the same. Yeah? But the difference is when you run a delete and you reinsert the data. If you delete a record from a clustered index and you delete it from a heap, it could be quite different. And its information is located on the page. So what I will do is I drop my table, insert 100 records again, and see where the data are located. Okay, my computer says it's time for dinner. I think so. Why did it work?
In one of the
No, I didn't. Let's see. One moment. Yeah, seems, yeah. Every time again. No. So. And the window, yes, exactly, yes. Sorry, that was my fault. Let's see, I think it was in this one. No, this one too. When I close the window, I should think that it will. Yeah, this it was. No, thank you. Every time. So I promise not to use the transactions again. The dedicated transactions again. Okay, I insert 100 records. Get the physical location where it is. I see the 168, and clear the lock. Okay. Now I clear. Delete from a heap. It's a very simple thing. I delete one, and that's it, and it consumes 460 bytes. Final, ready. Okay. What is important with the delete in a heap? The record or the slot will not be reallocated by another one. So that means, did I do the row? No. What happens overall? God, for God's sake, once again. So I made the mistake. Delete. See what happens, and I commit it. It's clear. So what happens overall is very simple. The only thing what occurs is it was a delete rows, this one here. And what you can see is that it consumes the complete record itself. It sees the information, this record has been deleted. Okay, so now I run a checkpoint again. If I delete records from a complete page, what do you think? Is Microsoft SQL Server so intelligent to say, hey, it's quite simple to erase the whole page? No, it isn't, because delete is not a bulk command. Delete means always, and this is really, really interesting and quite important to know, that you see it's 10K of transaction log, which has been produced. So, and what you see is when you select the operations, what happens inside, every single row is a dedicated transaction step. So if you delete hundreds of thousands of records with a delete operation, you don't have to wonder when your transaction log will explode. Yeah? Delete is a fully locked operation. You can't handle it with a bulk operation. Unfortunately not. This is the most important thing. If you delete the complete record, the complete table, it's always the same. Every single record will be locked. Okay, delete in a clustered index. Okay, now we are finished. I release you to dinner then. It's nearby the same. I create a new table, get the information about it. Okay, it's 178. And now, what I'm doing is, I delete one record, but before I will do this, I have to start this here. Come on, this. Yeah, this is okay. Now in the background, there is a script running, quite simple. It checks a special operation, which is an internal operation. This needs to be known in a clustered index. This is the way it's working. What I'm doing now is I start a transaction and delete my record. Okay. See the amount of data. It's quite simple. It's only 476 bytes. Okay, the very cheap one. And now I commit it. And what has happened? I have to. Already I see it. It's 178. Hope it's the track. It doesn't 178 because it was the number 5. See what happened? Number 3, 4, and the 5. Was it? Yeah, ID is 5. This is crazy. I would expect a ghosted record. Let's see, the record is there, but yes, here it is. This is amazing. I've deleted the record, but it's physically on the page, always on the page. This is a very efficient way what Microsoft SQL Server is doing. And the moment you delete a record from a clustered key or from a clustered table, the record will not be physically deleted because it's time-consuming. Think of the lazy operator. Do as less work as possible. And what the system is doing, it's saying, hey, this record is currently not available for anybody. So if you run a select on the table, on the page, this record will not be deleted. And what the system will do in the background is a background task. It will run a background task called Ghost Cleanup. I think once a minute this task is running, and this is checking, are there any pages where we have ghosted record, and at this moment these records will be deleted from that clustered index. This is a very efficient way, because for you have to think about, if you run a delete on a table and you have delete only one row, what is for you the most important thing? To release the locks. The moment you have locks on the table, it needs an exclusive lock on this row, and that means the SQL Server is, the most important thing for the SQL Server is to release the locks as fast as possible. And that's the reason why the record stays on the page and the background task take care of it. Pretty cool thing. Yeah? So this is all about DML in a very, very fast, unfortunately, way. I hope really that you, by the way, enjoyed this session. Unfortunately, it was too short. I expected 75 minutes. I got 60 minutes, and I produced nearby 80 minutes. So very sorry about it. I hope you enjoy the dinner further. Thank you very much.